This paper introduces moving gradients, a path-based method for plausible image interpolation. In this example, there are 90 frames in the original clip. If played directly, the clip takes 3 seconds. By separately interpolating between each frame of a video sequence, we can create a slow-motion movie. Our method can produce a smooth interpolation at any frame rate, preserving the frequency content of the input images. Here we introduce 8 intermediate frames and hence slow down the clip 9 times to play in 27 seconds. Notice the non-rigid motion of the head and milk cup. Also note that the occlusions with the truck and the background are handled properly. We now compare to the commercial software package Adobe After Effects. Notice the blurring and ghosting problem near the face and hand. In addition, we also compare with the interpolation by an optical flow method. Again, notice the blurring and problems near the occlusion boundaries. Our method uses a path-based framework. Here we show a didactic example with 2 input images A and B, between which we want to interpolate. We now show 2 input images again, along with 3 interpolated frames. Let's consider a pixel P at the same location X and Y in these images. To get a value at P for the interpolated frames, we borrow the intensities of the pixels from the direction opposite to the motion. For the first interpolated frame in the sequence, we borrow the intensity of the pixel to the left of P. For the next frame, we again borrow the intensity, but now from a pixel still further to the left. Key to our algorithm is to determine an optimal transition point at which to start borrowing the intensities from the second input image B, and the interpolation continues in the same fashion. The pixels from which we take intensities for the interpolated frames form a path in the input images. The path starts at pixel P in image A, moves through the pixels in image A, makes a transition to image B, and then moves through the pixels in B to reach P. The transition occurs at the point where 2 images agree with each other. Instead of moving the pixel values, we actually move the gradients for visually better results. We now compare our method with the optical flow methods from the Middlebury website. Here we show the input images for the backyard dataset along with our interpolated video. We also compare with the 10 highest ranked algorithms on the Middlebury website. In the simpler regions of the image, all methods, including ours, perform well. However, when we zoom into complex regions with occlusions, differences are apparent. Note that we are able to keep the ball intact and handle occlusions correctly, whereas all other methods split it into 2. Note the blurring of the feet in other methods. We preserve the frequency content of the image. A second application of our method is view interpolation. In this example, we show 2 input frames of a static scene with different viewpoints. Notice the difficult occlusion regions in the foliage. We are able to produce a smooth video that handles most occlusion gracefully. We now show another example of temporal interpolation of videos. This sequence is challenging due to the complexity of the motion. Note the people on the beach, the waves on the background, and even the panning of the camera. Our method is able to produce a smooth interpolation, or slow motion playback, shown here at 1/7 the rate of the original video. A final application of our technique is to animate still photographs. Here we show 2 still images of a yawning cat, which we downloaded from the internet. We are able to bring these images to life by creating the interpolated frames. The animation looks quite natural. Note that our method is fully automatic and does not require any user-specified correspondences or 3D models. Here we show an interpolation between 2 original still images of a face captured by a digital camera. We are able to capture the complex deformations of the face. We now show interpolation between images of normal and surprised faces. Note not only the changes in expression, but the head movement as well. Finally, to take this one step further, we represent images of 4 different face expressions: normal, smile, wink, and smile plus wink, as 4 vertices of a square. We can interpolate along the edges of the square by interpolating the input images. We can interpolate inside the square as well by interpolating the interpolated frames themselves. Note that the interpolation looks physically plausible even inside the square. In summary, we present moving gradients, a path-based method for plausible image interpolation with application to the temporal interpolation of videos, view interpolation, and the animation of still images.